And I think you should be good to go. Yeah.
Okay.
Yep.
All right, thank you, everybody. Our speaker today is virtual, which is fine. He's basically up in Ohio. So Joey Smith is our presenter. He is a research scientist in the Department of Food, Agricultural, and Biological Engineering at The Ohio State University. He has his PhD in interdisciplinary environmental sciences and a dual bachelor's and master's of science degree in basically the food and agricultural biological engineering, but he's also got a BA and master's in Mandarin Chinese. So hopefully he's going to speak in English today, but he clearly has the capability of doing otherwise. So Joey's work blends watershed scale monitoring and community-based approaches to stormwater management, aiming to make green infrastructure more effective and inclusive. Joey has conducted research focusing on quote unquote sponge cities and street side bioretention as a visiting scholar in Wuhan, China. And then also Luleå University of Technology in Sweden. His current research centers on tracking the hydrologic performance and water quality benefits of large-scale green infrastructure and wetland projects across Ohio. And so that's what we're going to hear about. So Joey, take it away.
Sounds great. Thank you for that introduction. And thanks to Dr. David Kaplan for the invitation to speak today, and to your guys' center, the Odom Center for Wetlands at University of Florida, for putting on this seminar series. So I kind of used your guys' seminar title of Water, Wetlands, and Watersheds to center my talk today. So we'll be talking about quantifying the hydrology and water quality efficacy of large-scale wetland and green infrastructure projects here in Ohio. And you'll see, I think the story here in Ohio is pretty similar to what's going on in Florida. All right, so for water, I'm going to start by talking about Ohio's water history. Then for wetlands, I'm going to talk about the Williamsburg Off-Channel Wetland Project. That's down in Cincinnati. And then for watersheds, I'm going to talk about the Blueprint Columbus Project, which is in central Ohio in Columbus. So for Ohio's water history, Ohio is located just south of the Great Lakes. We have Lake Erie to our north and the Ohio River to our south. So here's Ohio. And water to the north of our state drains to Lake Erie. Water to the south of our state drains to the Ohio River, then into the Mississippi, and then into the Gulf down by you guys. So in 1803, when Ohio first became a state, Northwest Ohio was basically untouched and only known to Native Americans and some explorers. But development in this Great Black Swamp area was delayed nearly 100 years behind the rest of the state. And that's because of that Great Black Swamp. Some historians called it an absolutely terrifying wilderness, one that swallowed wagons and horses. So if you think about some of the words that are in the English language that are related to wetlands, when we say I'm swamped or I'm feeling bogged down, swamps and bogs are both other names for wetlands. And it's kind of ingrained in our English language that wetlands have a negative connotation. And it's sort of because of that westward expansion dialogue. So in 1835, there was a Toledo War where Ohio and Michigan had a dispute over who was going to own this Toledo area. And it was a bloodless war. So no blood was shed, but the result was Ohio got Toledo and Michigan got the Upper Peninsula. So if you ask me, the Upper Peninsula is a pretty nice win. But why I'm bringing up this story is while the Ohio militia was going through our state, they came across the Great Black Swamp, which greatly delayed the militia in going to the Toledo area because of that Great Black Swamp. So this eventually led to the swamp's demise because our government said that they were going to allocate lots of money to draining the Maumee and western Northwest Ohio areas wetlands. So here's a historical marker talking about the draining of the Great Black Swamp. And it has become one of the most productive regions in Ohio in terms of agricultural production because it once was a swamp, a wetland. So some consequences of draining the Great Black Swamp. Now we have lots of eutrophication, especially in the Western Lake Erie Basin. Around August, you don't really want to swim in Lake Erie anymore because of toxic algal blooms, and the nutrients cause fish kills, algal blooms, and all sorts of issues to tourism, coastal economies, etc. And what really made the news was in 2014, this closed Toledo's water supply in 2014 for about 2 weeks. So Toledo, that same area that I mentioned in the dispute, it's got some consequences from draining the Great Black Swamp. And I want to kind of tie this into Florida a little bit with the red tide. My understanding is that it's caused by lots of nutrients going into the ocean. The same story is happening here in Ohio. We have lots of nutrients going into Lake Erie. It's a very shallow area, so it's prime recipe for algal blooms. So in Ohio, we have something called the H2 Ohio statewide project, and all these different dots are wetlands that are being put throughout the state to sort of make up for the wetlands that have been drained. And the first project I'm going to talk about is the one way down to the south in Clermont County. It's the Williamsburg Wetland project. You'll notice that most of the projects are concentrated up in the Great Black Swamp former area, but the project that Ohio State is really monitoring is this D down here, the Williamsburg Wetland project. So that's what we're going to start talking today. So the Williamsburg Wetland is an off-channel wetland, and this work is Sarah Walentine's master's thesis. So I wanted to give credit to her. She did a lot of great work, and she just got her dream job where she'll be designing these sorts of wetlands. So if you want to learn more about the wetland, here's a QR code that will take you to YouTube. And it was a video created by Clermont County, just introducing the wetland and how it works. I think it's a little bit basic and it shows lots of pictures. So if you're interested, you can also just type the quoted area into YouTube. So a little bit of background on this wetland project. It's located in Southwest Ohio in Clermont County, just east of Cincinnati. It's in the floodplain of the East Fork of the Little Miami River. The drainage area upstream is 234 square miles, and it's 64% agricultural land use. So this is an ag project. Among other important uses, the East Fork of the Little Miami River provides public water supply. There's also lots of recreation that happens in the area, so there's lots of contact with people in the water. It has a very gradual slope in the area. And prior to the wetland construction, the land cover was primarily a forested riparian zone. From the 1950s to 2018, the river was dammed just downstream of the wetland location to create a reservoir to provide drinking water for the village of Williamsburg. The dam removal occurred in November 2018, and then the wetland was constructed in 2022. We began monitoring it in April of 2023. So you'll see that a big motivator of this was that there were harmful algal blooms in the East Fork Lake, also called Harsha Lake. And you'll see a posting there saying, "Danger, do not recreate in here," because of the algal blooms. Phosphorus is limiting in nutrients in fresh water. So the East Fork Watershed Cooperative Mitigation Strategy was created to emphasize reducing phosphorus. And phosphorus comes from some of that fertilizer applied to ag fields and other sources. So the Clermont County Soil and Water Conservation District sponsored a large construction wetland project, and that's the subject of the research we're presenting on here today. And there's a very limited body of literature about this type of wetland. So here are some drone pictures of the wetland. It was once a drinking water reservoir that was sitting abandoned. So the Clermont County made use of it, and I'll explain a little bit more of how the wetland works. So the research objectives of this study were to quantify the sediment and nutrient load sequestered by the wetland. This is a storm-driven system. And for water quality, we measured nutrient and sediment concentrations and loads to determine the treatment effectiveness. So here's an overview of how the wetland works. To the bottom of the picture here, you have the East Fork of the Little Miami River. Water is diverted into this wintering pool area when we have high enough storm events. Whenever the stage of the river exceeds 3.5 feet, that's when water enters this wintering pool that sort of serves as a forebay. There's a 24-inch pipe with a flap gate that diverts water into this reservoir, and then water is very slowly let out of the reservoir through the gut of the wetland. And it's designed for a large storm event over 10 days to very slowly allow the water to go out of the reservoir. Also, the water can go directly to the gut of the wetland through this bypass area. The wetland hydrology is pretty complicated. This cis-in area was designed to be the inlet, but also this cis-out area that was designed to be the outlet. When the river stage gets high enough, the outlet serves as an inlet and an outlet. So we've equipped this wetland with 5 sampling locations here at cis-in to capture the water coming in, 1 at the res-in to see the water going into the reservoir, another ISCO sampler at res-out, another at the bypass, and then finally 1 at the outlet. So we've been doing some ISCO water quantity and quality sampling. And then also throughout here, we have some water level U20 loggers to see the water level. And those are at 7 different locations throughout. The gut is a 2-stage ditch and is very sinuous. There were logs that were taken from the excavation site and put into this 2-stage ditch to allow the water to slow down. We also have an on-site rain gauge to track the precipitation at the site. So we had 2 different phases given the complex hydrology of the system. The first phase was the rising limb, and then the second phase was the falling limb. So water coming into the wetland, since we had water coming in and out of the inlet and coming in and out of the outlet, we just decided to have like a rising limb, and we sampled at 3 different locations: the system inlet, the reservoir inlet, and the bypass on that rising limb. And then on the falling limb, we sampled at the reservoir outlet and system outlet. And the stars on the hydrograph show where we took the samples. Due to the very low site gradient and backwater flowing into the system, the pollutant, influent, and effluent samples are collected according to sampling location. And the effluent samples are composite. And we were able to calculate load using a stage storage model. Since we didn't really have water entering from a pipe and it was more of an open channel, it made it a little bit complicated to use auto samplers to quantify. So we ended up using a stage storage model and the water level loggers throughout the system. So although the calendar year of 2023 was our first monitoring year, the water quality sampling equipment was not set up in time to capture the wet season. So in our monitoring time, we've only gotten samples from January through May. The rest of the year has been too dry and the river stage hasn't gotten high enough to create a sampling event. But in the calendar year 2024, there were 66 on-site rain events, 8 of which were associated with wetland inflow. So you can see here, those 8 numbered events are the ones that allowed inflow to happen into the wetland. This wetland was designed to get more inflow events, more in the range of like 30. But since 2023 was so dry, we didn't see any inflow events in 2023. Also, a lot of sedimentation happened at the inlet. So I'll show you that here. Here's the inlet of the wetland. You have the East Fork of the Little Miami River, and it was designed for the river to get to a high stage and then enter the wintering pool. But over time, in the second picture, you can see that the river carried a lot of sediment and made the required river stage higher and higher. So it was planned to have 30 events, but as the river stage got higher and higher, then we only expected 20 events and we only saw 8 events enter. So I've gotten to be down at the wetland to see the Parks Department excavating out the inlet because of all that sedimentation. It's a really big job. And they're currently submitting some grant funding to redo this inlet so they don't have to excavate so much water, so much sediment with all that sedimentation happening. So here's the summary of the 8 events that created inflow in 2024. These treatment volumes are extremely large for a stormwater practice, and inflow events are highly seasonal and are presumed to be a function of low temperature, low evapotranspiration, and high soil moisture content across the watershed. There's also a positive correlation between on-site precipitation and inflow volume, and we can see that the wetland inflow occurred with on-site precipitation depths that are greater than 0.65 inches. The reservoir inflow volume compromised between 36 and 57% of the total system inflow volume. And the reservoir residence time drove the overall system residence time. So you can see that these volumes of water are very large. And then let's look at the sediment. So significant reductions for concentrations occurred at all locations. And a lot of the sedimentation happened in that wintering pool, which we could definitely see by all the sediment that accumulated there, preventing water from inflowing. The bypass loads were calculated using the gut volume, so significant load differences obscured between the bypass and the outlet. So on the left of this blue line, you can see the influence TSS concentrations are higher than the outlet, the effluent, in terms of concentration and in terms of load. We're seeing very large load reductions. And same story for total phosphorus. For the influent, you can see we have higher concentrations and loads in comparison to the effluent. So processes that made this happen, a lot of phosphorus is particulate bound. So we had sedimentation occurring in the wintering pool. And then for the dissolved form of phosphorus, which is really concerning for eutrophication, there was additional treatment occurring in the gut of the wetland. For total nitrogen, you could also see some significant reductions, but here the gut of the wetland had more of an influence. Sorry. All right, so here are the load retention efficiencies for all pollutants and wetland components, with the overall system efficiencies in the top row. The wintering pool, which is part of the gut, is driving the overall system retention efficiencies for TSS, total phosphorus, and dissolved phosphorus. And the wintering pool is also providing the only significant ammonia load retention for the system. Total nitrogen treatment efficiencies are comparable for the different wetland components, with the wintering pool providing the most nitrification and retention of total organic nitrogen. And sorry, this presentation was made by a colleague, so I'm not as familiar with this part, but the second part I'm more familiar with. I just really wanted to highlight the huge load reductions that we're seeing from the system and the different parts where that retention is happening. All right, so conclusions for this first part. There were highly effective sediment, phosphorus, and nitrogen load reductions. The wintering pool was great for particulates, dissolves phosphorus, and nitrification. The reservoir enhances nitrogen treatment, and the storage volume and long residence times are key for the denitrification processes. The gut hydrology and load removal are very difficult to quantify, given that it's this 2-stage ditch open to the elements. with water going in and out both ends. We saw excellent water quality performance. And the treatment is expected to improve. We're continuing to monitor this wetland here in the calendar year 2025. Every quarter, we are collecting soil and plant samples to try to do kind of a mass balance of nutrients within the wetland. And Sarah did create a model of this wetland. So in order to create the model, an aerial survey was done. We had a drone fly over the system and use that to create some DEM. Design drawings were used to help create the model, so we knew the different dimensions of the pipes. And for the Manning's coefficient and the land cover, we used the National Land Cover Database. So for hydrology, there was a USGS gauge for the river stage just upstream of our practice. And then we also had hydrology data from our 5 ISCOs throughout the system. And then we had 2D unsteady flow modeled through HECRAS, and we were able to model the 8 wetland inflow events that occurred in the calendar year 2024. And Sarah did some qualitative and quantitative model fit. I don't have time to get into that today, but the model did perform very well. So Manning's N is a key parameter in this model. These are the Manning's N's values determined through literature and field observations. And you can see we have different Manning's N values for the different portions of the watershed. And we conducted unsteady flow analysis. There were 8 storm events modeled with unsteady flow using 2D flow in HECRAS. And I wanted to show how the model looks. Oops. I'll start with water level. So this was for the 6th event that occurred in 2024. It was a 1.4-inch rain event. And you can see water entering the reservoir, and then it just went through the sinuous part of the gut. And now it's entering into the stream at the system outlet. In this model, the peak river flow was 6,780 cubic feet per second. And the peak depth of the gut got to be 4.8 feet here. So there's the water level model. And then I'm going to play the velocity model. And this was a medium level event. We did have some smaller events that caused inflow into the wetland, but I thought this was a good way to show how you can use this field data to create models. And then now that we have this calibrated model, we're able to do different scenarios and understand how sediments transported through the system if we add. We have another PhD student who just started on this project, and our goal is to look at sediment transport throughout the system. So it's really great to have this calibrated hydrology model. So some conclusions from the modeling part of the Williamsburg Wetland project. HECRAS 2D is a useful tool in this type of floodplain. The simulation is successful for all events. There were very good Nash-Sutcliffe coefficients for 6 of the 8 storm events with very low bias. So the 2 storm events that were more difficult to model were back-to-back events just because of the initial condition assumptions. So that's another area for improvement in this project. And here are some of the sources of model variability, especially with initial condition, as I just mentioned. But we could also improve Manning's N at a higher resolution. So that's the first project of the Williamsburg Wetland. You can see that in response to draining wetlands back in the 1800s, Ohio was really investing a lot of time and resources into putting these wetlands back throughout the state, especially in Northwest Ohio. So speaking of big watershed scale projects, this is called the Blueprint Columbus project, and this is the second one I'd like to highlight. Instead of the previous project, which was more in a rural setting, this is in an urban setting. So if you're interested in more about this project, you can scan the QR code for a YouTube video. And you can also search it in YouTube for Blueprint Columbus 2016. So here's Columbus. And in Columbus, we have combined and separate sewers. We have combined sewers in the center of our city, and we have separate sewers in the suburbs and the outskirts of the city. So we had too many sanitary sewer overflows into the Olentangy River, and we also had combined sewer overflows. So we had 2 separate consent orders because of too many overflows into our waterways. So in order to respond to the consent order, which is a lawsuit, the Ohio EPA sued the city of Columbus. So in order to respond to this lawsuit, we decided on gray infrastructure to respond to the combined sewer overflow consent order. And we decided on green infrastructure to respond to the sanitary sewer overflows. So the response to the SSO consent decree, the project is called Blueprint Columbus. So Blueprint Columbus is a massive project that started around 2015 and it's set to go through 2045. This map shows different areas throughout the city, and they're all expected to get green infrastructure from now through 2045. This is the area that we conducted our study in. It's called Clintonville. It's a neighborhood in Columbus, and we have the Olentangy running along its east side. And you can see on the map, they have an interactive map so people can see the different phases of the project and its progress. But these different shadings are rain gardens, different styles of them, and pervious pavers throughout the different watersheds. They did also install a big wetland down here in the Park of Roses. So in this watershed down here at the bottom, we have hundreds of bioretention cells that first treat the water, and then additional treatment is provided by a wetland downstream in the park. And here are some of those pictures. So the blue shading is sort of like the top picture. It's a big regional basin where water is piped in from the sewer system. And then the green are called bump outs. So they sort of go onto the road. They collect water that runs along down the curb. And then there are pervious pavers. Entire streets are being turned from impervious asphalt surfaces to pervious pavers. So Blueprint's a little bit complicated. There's 2 different phases, and I'm just going to be really focusing on this post-GI phase 1. So the first phase is green infrastructure was installed into neighborhoods. And then the second phase, these additional infrastructure improvements, which we call AI squared, additional improvements, were conducted. So downspouts from homes were redirected into the rain gardens. Sewer laterals were lined, and the goal here was to prevent infiltration and inflow into the sanitary sewer. And then homeowners who did not have a sump pump were given a free sump pump. And so this phase 1, the main goal was to reduce total suspended solid loads by 20%. The city had that written as a goal of their green infrastructure. And then for the second phase, the goal was to prevent infiltration and inflow into the sanitary sewer. A lot of the pipes that go out of homes in these areas are clay pipes. It was a more legacy area with older homes. So people were experiencing basement backups as tree bulbs and other obstructions caused sanitary sewage to back up into people's basements. So 2 main goals of this Blueprint project: reduce total suspended solids concentrations by 20% and to reduce infiltration and inflow into the sanitary sewer. The broad goals of Blueprint align with the OSU research objectives. So Blueprint wanted to control stormwater flows. So this is more hydrology focused, improve water quality, provide habitat, improve property values, and stabilize neighborhoods. There was also the want to create more jobs in neighborhoods by having people maintain the bioretention cells and to maintain the permeable pavement. And we've gotten a lot of papers out of this. The first 3 papers are more on the left side are about hydrology and water quality. Then on the right side, we have papers about habitat, public health, and social perceptions. But for today's presentation, I'm really going to focus in on these 3 papers that are up here. which are looking at hydrology and water quality. So the research objectives of the study were to quantify the hydrology and water quality changes that occurred from green infrastructure and to discuss some of the reasons. And this work was done to address some existing knowledge gaps. So this is a very massive project on the scale of larger than 10 hectares. There have been some other studies looking at watershed scale installations of green infrastructure, but they are at very small scales with maybe just a couple of practices installed, but we're talking about an entire neighborhood. So the main two kinds of green infrastructure installed into neighborhoods were bioretention and permeable pavement. And I wanted to introduce you to the bioretention design in these neighborhoods. So the bioretention and green infrastructure broadly in this area were designed to treat water quality, the water quality volume, which at the time was 0.75 of an inch. But as we get more extreme rain events, Ohio has since updated its design water quality volume to 0.9 of an inch. Anything beyond that water quality volume is designed to just go into an emergency overflow or just bypass the system entirely. So a little bit about how bioretention works. You have stormwater entering the practice. There's a designed bioretention soil media. In Ohio, we have between 80 and 90% sand, and then the rest of it is native soil, and it's amended with compost, 2 to 5% organic matter by mass. So some of the processes that happen in bioretention cells, you can have exfiltration happening into the groundwater, you can have evapotranspiration, and sometimes they add an upturned elbow, but you'll see here that we didn't have that in Columbus. So in Columbus, we had to have an underdrain for our bioretention systems because we have clay soils here. And if you don't have an underdrain, then it would just turn into a wetland. It wouldn't drain very well. And then the city decided to not have an internal water storage zone. So for the green infrastructure side of the project, they only wanted to reduce total suspended solid loads. If you add this upturned elbow, it would have created more hydrology benefits, but for this side, they were only really interested in TSS reductions. So one of our suggestions after this study is if they wanted to see more hydrology benefits, perhaps they could consider this upturned elbow, but that was not the case here for Blueprint. Then for permeable pavement, the city decided to go with permeable interlocking concrete pavers. So you have bricks and the stormwater runoff enters through the interstitial spaces. There is an underdrain that still conveys to the storm sewer and then downstream waterways. But here there was some opportunity for exfiltration again into the substrate. But you can see here with permeable pavement, there's no bio in terms of plants, but there are some microbes still in that very rocky substrate. So in order to do this study, we had to use the power of a paired watershed design. We wanted to say that the changes we were seeing in hydrology and water quality were due to the green infrastructure and not due to seasonal or annual changes that we're seeing in the watershed. So we had to have two watersheds, a control and a treatment. And then we had two monitoring periods, the calibration before any green infrastructure was installed, and then the treatment, which is after any green infrastructure was installed. And like I was saying, this accounts for the year-to-year and seasonal climate changes. So here is our area that we're working with. We had the Olentangy River to the east. The yellow shows the three watersheds that were in our study. The purple are the outfalls that we monitored at. The different green areas are bioretention areas. And then orange is permeable pavement. You can see that these were all very close in proximity to each other, within 1 kilometer of each other. So our control area is called Beechwold, and it had no green infrastructure. You can see that there's one street that ended up having green infrastructure installed, but that was not part of the plans and we had to adapt. But we were able to decide that it was such a small area of the watershed being treated that we thought this was marginal. We did have 2 other control watersheds on the other side of the river and decided that Beechwold was still an effective control despite that one road getting some green infrastructure installed. So Indian Springs had 5 permeable pavement roads. You can see that in orange, and there were 32 small bioretention cells installed throughout the watershed. These 32 bioretention cells treated about 70% of the imperviousness. And then Cook Glenmont, while there were only 3 large bioretention cells installed, they were those very big regional ones, and they still treated 66.5% of the impervious area. And I wanted to highlight these percentages treated by green infrastructure because you'll see when I talk about total suspended solids results later that the percent imperviousness treated by GI is related to the TSS concentration reductions that we saw. So for our monitoring, we had continuous rainfall and flow monitoring, and we monitored at 4 different outfalls. You can see those outfalls here. So these are the same outfalls that are in purple in this map. And we equipped those outfalls with area velocity meters. We also had the sample intake inside those, and they were programmed to be enabled whenever the level above the sensor went up by 0.2 feet. That was simulating a rainfall event. It was just indicator that it's raining in the watershed, the water level got higher above that. And we analyzed for different nutrients, sediment, etc. So the statistical method that we had to use here was called an ANCOVA. And since we used that before after control impact, you can see that before is plotted here in the black line, after is in the dotted line, and then the control and the impact watersheds are plotted against each other. And the percent difference that we saw in hydrology and water quality is called the least squares means. So here are some results about hydrology. So in this watershed, we saw around about 20% runoff reduction provided by the bioretention and permeable pavement. That was in phase 1 of the project. So compared to the pre-green infrastructure phase, the post-green infrastructure phase had 20% less runoff produced. But then after the next phase, where additional stormwater infrastructure improvements were added, for example, the downspout redirection, the sump pumps, and the lateral lining, there ended up being no change from the pre-green infrastructure. So to kind of sum up the hydrology story, there was a baseline water level, water depth. Then green infrastructure was installed, the runoff depth reduced by 20%. Then we added more water to the system with these additional infrastructure improvements. So we went back to the pre-green infrastructure phase. So there was like no net harm in runoff depth. Then looking at total suspended solids, here we saw a 62.1% reduction at Cook Glenmont. That's the area that had 3 bioretention cells. And that was in control, the ANCOVA analysis. So we were able to say that the TSS reductions that occurred were because of the green infrastructure, not because of other things. So this is the same data, just presented in a different way. We had the control Beechwold here. We saw a 62.1% reduction in Cook Glenmont, which is the same thing I presented back here. So this reduction was a 62.1% reduction in reference to the control site. In this other watershed, Indian Springs, we also saw a 69.7% reduction. And I found an interesting relationship related to the amount of imperviousness treated by green infrastructure. So the percent of the watershed imperviousness treated by green infrastructure was about equal to the percent TSS concentration reductions that we saw within a 5% margin. So if you are a planner trying to get rid of a certain TSS concentration, you might consider how much of the impervious area you're treating by green infrastructure. It's, from what we found, closely related to the impervious level that you're treating. And the city's goal was to reduce TSS loads by 20%, and they far exceeded that just from the first phase. For heavy metals, there were significant reductions in heavy metals at one of the treatment watersheds only at Cook Glenmont. So we saw copper concentration reductions, and then we saw load reductions for 4 of the metals. And I've been thinking long and hard about why did we see concentration reduction, heavy metal reductions in one treatment watershed but not in another. And I think I've found out why. So this Indian Springs area is the area that we did not see any heavy metal reductions. And so here you have water going along the curb line. It enters these bump outs, and then it just continues down the stream, and you have down the street. So you have preferential flow paths forming. You also have water very easily bypassing the green infrastructure system. So same thing here in picture C. The designers expected the water to make a 90-degree turn and then fill in this depressional area. I've been in the watershed recently, and I've seen that so much sediment has accumulated from a lack of maintenance that you're not really getting any treatment going in, making that 90-degree turn. So I think in these pictures B and C, I'm not really convinced that a lot of treatment was provided because just of how they were designed. They were designed just to treat a certain amount, and then the water keeps on flowing down the street. But then in this Clermont area with pictures D, E, and F, although it only had 3 bioretention cells installed, the water was piped in, and there was definitely sedimentation happening, and the water at least had some chance of getting in contact with the soil before it went downstream to the underdrain, to the overflow structure. So I want to talk a little bit more about copper. Copper is the only heavy metal analyte that we saw having a significant reduction in concentrations. So copper complexes with organic matter, and we did amend the bioretention soil media with organic matter. So copper that comes from breaks and roofing materials was able to complex with the organic matter inside of those Cook-Lemont bioretention cells. And that's why we saw reductions. So some conclusions for this blueprint project: the design, construction, and maintenance of green infrastructure systems are key to their long-term functioning. We have observed quantifiable effects of green infrastructure on the watershed scale. We saw significant particle removal far in excess of the 20% TSS reduction goal set by the city. We saw copper concentrations decrease, and we saw concentrations decrease for 4 heavy metals as well. So if you're interested in the rest of the story after these additional infrastructure improvements were installed, it's a bit complicated, but it is available publicly at this QR code. So I told a little bit of the hydrology story after these additional infrastructure improvements, but we're still working on telling the water quality story. So some overall conclusions from the entire presentation as a whole. Ohio's wetlands were drained back in the 1800s. That created some water problems like eutrophication. But now Ohio's investing a lot of time and effort into watershed restoration at big scales. And we're reconnecting rivers to their former watersheds, and we're installing green infrastructure into neighborhoods in response to too many outdated systems. So thanks for listening to my story talking about wetlands and watershed scale installations of green infrastructure. Here's my email for your reference, and I'd gladly welcome any questions.
Great. Thank you, Joey.
Thanks.
Room for Dr. Smith.
So how did you decide which neighborhoods you wanted to use for the second project? Were they just given to you, or did you survey them first?
Yep. So this project was a real construction project. So this neighborhood, Clintonville, was decided to be the pilot area. So we decided on Clintonville for that reason. But for the specific watersheds that we selected, we wanted to have them close in proximity to each other because that's a need for the paired watershed design, is that they need to be close in proximity. Also, we had to be able to safely access the outfall. So we did get some pushback from reviewers on our studies saying that our control watershed was a bigger surface area than the treatment ones, but it was the only watershed on that side of the river we were able to safely monitor. So we ended up going with that treatment watershed or that control watershed. And then this ended up being about 10 years worth of a project because we had to monitor for a period of time before the green infrastructure, after the green infrastructure, and then after the additional improvements. So sort of just because of calendar. Great question. Other questions?
So in this first project that you talked about, like in the south of Ohio, like that wetland, is it not like partly in the original meander of the river? Like it really looked like it?
So I think it was part of the original meander, and we were reopening that area to where it originally had meandered. So yes, it was an existing floodplain riparian zone that we just reintroduced the river to. Oh, I realized I went a little bit fast. My timer was saying 45 minutes, but that's when I had started the PowerPoint, so I rushed unnecessarily. But more time for questions.
That's good. We got some time for questions. Is there any online?
Well, I sort of have a question for you guys. Do you guys think the story of water in Ohio relates to the story of water in Florida at all? In terms of like draining wetlands? Like I know a little bit about the Everglades, but I want to hear more since you guys are in Florida.
I have an answer, but go ahead. Anybody have thoughts about the history of Ohio and the history of Florida? Go ahead.
I think it relates pretty similarly. I worked at Disney and Disney used to be like a giant wetland, and I know when it comes raining, we would have to literally get pumps and stuff to like get the water out. And I would see like all sorts of different things within the water. But I don't know about any like research projects to fix that. But I just know it's just like really nasty water that we're like trying to pump out and put in these giant containers. And then I don't know where Disney puts them after that, but that's what we end up having to doing when the parks are closed.
Any other
Thanks for-
thoughts? Joe, I think they're absolutely parallel. I mean, you know, the fates of the wetlands in Florida and the fates in Ohio are quite similar. I think that the scale of agricultural conversion, up there was very much heavily influenced by tile drainage systems and literally lowering the groundwater table. Here, it's been heavily compartmentalized, and the Everglades is really up to the fate of human determination as to what goes in and what goes out. So yeah, I think they're quite similar. And the urban issues, especially with green stormwater infrastructure, are quite similar as well. I mean, we're dealing with the same load reductions necessary. I think our infrastructure was placed a little bit later, so I don't know of any combined sanitary and stormwater systems in Florida. That doesn't mean there aren't any, but rarely are we having to deal with that issue. But basically just the stormwater infrastructure alone is not meeting oftentimes our designated uses. And so I don't know if you all have a process of TMDLs and impaired water bodies, and what we have is called basin management action plans. But you had the consent decree that triggered a lot of your response there. We have something similar that basically is driven by this statewide water quality monitoring, but that's triggering things like green stormwater infrastructure, agricultural best management practices, things like that at the watershed scale.
Awesome. It sounds like this is happening all over the world, because when I've been in China, I go there to study sponge cities, and they're adopting green infrastructure on watershed scales too. So it sounds like it's a global issue, all parts of the US and globally too.
And since we have one more minute, can you define a sponge city for everybody?
Yes, so sponge city is directly translated from Chinese, and it basically means that you're reintroducing sponge, which in this case is soil, into cities. So you're introducing rain gardens, wetlands, permeable pavement, sources of sponge back into cities.
So how do you say it in Mandarin?
海面城市.
Everybody got that? All right, thanks again, Dr. Smith. Last
Thank you.
another platform. Thanks, Joey.
Thanks.
All right, I don't have next week's speaker, but either way, be here.